Today, I decided I want to talk about. I recently got a request for visualizing survey data. This is something that a lot of students find challenging, and it's new to them, and staff as well sometimes. And as some of you may know from the emails we get, a lot of our students, especially undergrads in certain subjects, some like food technology and a few others, they typically do surveys for their project. But in a broader sense, from my perspective, what I've seen my whole career is that you have some fields that are very good at conducting surveys, designing the surveys, and then they have their own methods and standards for analyzing the survey data. But I have seen some quite shocking approaches to visualizing and analyzing the data. And for naive students, it's very, very difficult. Or if you're just building and putting the tools in your toolbox, building your skills, it's daunting because there are a lot of different approaches. Some of them are more technically correct than others. So I thought, since I got a recent request, I would do a session on a new library that's in the ggplot family in the tidyverse that is the easiest and very powerful way to analyze Likert data that I've seen. And I've used R for many years to do it. So I thought I'd do that today. And if you haven't heard of Likert data, I'll introduce what that is as well. Next week, I'm going to do something completely different and talk about a new model has just hit. I think over the past couple of years, some of my own research has been in computer vision. I've had a number of projects start up. One big one was looking at growth characteristics in tuber plants and potatoes. But I've had a bunch of other kinds of smaller projects with students as well. Everything from from some master students working on automatic classification of moth species on moth traps that take images periodically and then use an artificial intelligence to classify the species, to taking high resolution computer images from satellites and looking at hedge boundaries and the hedge state and the amount of carbon captured in hedges. Some hyperspectral images from plant development, and a few others. And I guess one that we've heard about in here from George Wager is her PhD looking at identify using AI to classify from video animal posture when they're feeding to determine whether they're sorting or some other aspects of how they're picking and choosing the nutritional intake from the food they're offered. Anyway, all of the work, I should say, that I've done up to now, and all the work that most people in this world have done up until about 3 or 4 years ago, was based on a kind of AI called neural networks. If that doesn't mean anything to you, or if it's something you've just heard of, but it's a vague concept, what I want to do next week is just kind of describe the basics for everybody who might be interested in this. But there's been a big change in the world. The large language models that we all use, ChatGPT and the others that we've been talking about in here, are part of the change. But an even bigger change is the technology underlying large language models, which is fundamentally different, works differently to the traditional neural networks that computer vision and other AI models were built on. And they're called transformers. And this is an idea that came out of Google Research Labs. The idea of transformers came out about 10 years ago now, 9 years ago. The paper came out. It's been cited like 100,000 times, the paper, in 9 years. And essentially, the new computer vision models are all using transformers, just like large language models, and they're much easier to use. They're much faster to train, and the entire world and all of industry and research will be using them sooner or later. A brand new model just came out from Meta, the parent company of Google, called SAM3. Everybody from agriculture researchers to computer scientists to Marketing people are all using vision transformers now. And so I thought we would do a session on it. I'm very interested in this new model. It's supposedly super easy to use. I've already looked at the architecture and how we can do it in just a 1 hour session. So I'm looking forward to that. Um, First one back after the Christmas break, I'm going to look at a practical one for students and other interesting people, how to design a statistical analysis plan. I'm going to set myself the challenge. I don't know if I'll achieve it. Maybe a good first session would be just describing what a statistical analysis plan is and why it's useful to you for your PhD. Many students make them anyway for their PhDs, but I think all researchers should use them before they collect any data for any project. So I'll explain why that is, and as a challenge to myself, I'm going to attempt to set up an AI environment to generate a statistical analysis plan if you input details for your project. So we'll see if I can do that. Anyway, today we're talking about visualizing survey data in R. If you'd like to follow along in the slides, you can do that right now. So I'm going to go ahead and begin. Now, what is Likert data? I'm going to show you a little bit about setting up a project like this. This is a multi-file project. I'm not going to go through all the details technically in GitHub, but maybe I'll make a little argument about why this might be a good idea for you to think about doing, and also show you how to set up a project, whether you use it on GitHub or not. So even though this is a tiny little project, I took the minute extra step of setting it up just like I would a professional data analysis project for either small data sets or large ones or anything in between. And then most of the time we're going to spend today in R looking at this GG Likert package and function and just some of the variations that you can do. And along the way, I'll talk about some of the standards for graphing survey data and what people do. And the thing I like about GG Likert is that the other solutions I've used in R require require me to be aware of all the little details for information that's extracted from survey data, and I have to manually implement that. And it's doable, but it does take a little bit of effort. And the thing I like about GG Likert is they've automated almost all of the real nice ways to visualize that kind of data in just a simple little set of functions, just primarily one function. Okay, so that's what I'm going to do. If you've never heard of Likert data before, it was invented by this guy, Rensis Likert, and I was, to use a phrase, tickled pink to find these two pictures were the first two pictures that jumped up from him. One on a day when he was unhappy, and then another day when he was tickled pink. I just love these two pictures. I don't know anything about his career, but he is quite famous for the design of collecting survey data. So you design survey questions, and it's the kind of survey that you're probably familiar with. The bigger framework for these surveys is to measure agreement or disagreement, to measure the frequency of responses, or to measure satisfaction or dissatisfaction. Let me give you one example that's a big famous example that some of you have probably actually been subjects in, probably more than once in the UK if you've done your education here previously. And that's the National Student Survey and the Graduate Student Surveys. The National Student Survey I know more about. It's run about, this stage, it's run about a little bit more than 15 years. I've published a number of papers analyzing the national data set some years ago with a friend of mine. Once it had run 10 years, and we did a lot of detailed analysis of it. And one of the things that I did personally was created a benchmark metric for comparing universities. A lot of universities like Harper Adams just compare it, just look at different courses in the university. But of course, the national statistics compare universities, and that's where the league rankings come from in part. And what they do is they ask well, in the old survey anyway, 26 questions that measure satisfaction or dissatisfaction about 6 different core concepts. My point of going through that little bit of detail is that there's a bit of design that goes into designing a survey, I'm not really going to talk about elements of the design, but if you don't adhere to the some of the elements of design, one element of design is to formally lay out what it is you want to learn and what the shape of the sentiment is that you want to learn from it. So again, going back to the National Student Survey data, they want to learn about specific topics, about the quality of teaching, about the resources available for students, about the organization. And, you know, I said there are 6 of them. And traditionally, you would identify these, identify whether you know, what the quantity is, whether it's agreement with some statements or whether it's satisfaction or something like that. And then you would prepare a number of different questions within each of those topics that are similar but distinct, that build in some redundancy. This is an important architecture part of best practice for these surveys. Anyway, in my experience, a lot of people ignore that when they're doing these surveys. They parrot or emulate other surveys they might be familiar with and do haphazard design of these surveys. And it makes it harder to analyze. If you have that structure that you formally laid out, it makes it much easier to analyze. All right, get it on off my soapbox now. We traditionally think of this as ordered categorical data. So you have a range of like up to dislike or dissatisfaction up to satisfaction and so forth. And we use them in all sorts of things. Marketing and social science is probably the big one, but education is also a real big one these days, and it's just getting bigger as a thing unto itself. Mentioned we call this an ordinal scale because the categories have number and an order. And one of the downsides of this is that with ordinal data, we assume the amount of satisfaction between each category is the same. But a downside is that we're guessing about this. So the bigger gambit is that for the researcher to assume that the amount of satisfaction between each of their categories is the same. Well, it's easy for a researcher to say, yep, I assume that, that's fine. But the problem comes when you start to survey the population, sample the population, and it's actually your assumption, not that you're happy that that's true, but that each of the subjects you sample understand that to be true and answer accordingly. And the real problem arises when there's systematic bias, let's say between males and females. You know, maybe maybe a gender or maybe a cultural artifact from your sampling is that that one category, one subcategory is I've just noticed I'm covering Leichert's happy face with my big head. I'll just let you see that real quick. There we go. That's Leichert and his sad and happy face. An artifact is that different subpopulations may view that differently. So they may make maybe it could be socially unacceptable to be negative, and so to express dissatisfaction for some subgroups. And that's an example of why this is an important but often violated assumption. Commonly, when you analyze these things, it's real common for me to see people use means of responses. That if it's on this Likert scale with these categories, they might convert the categories to a numeric scale and then just analyze the numeric scale using means with an analysis of variance or something similar. That's generally frowned upon. It's extremely frowned upon by some statisticians and scientists in certain fields like psychology. It's a little bit better to use medians and modes. So for technical reasons I won't get into. And using non-parametric tests is also an improvement over analysis of variance for the reason that, there can't be a Gaussian or normal distribution for this kind of stuff. And you can also analyze individual questions, or you can analyze analyze those categories that I referred to within the survey instrument, as people who design surveys call them. And you can also do counts and frequencies with proportion tests and even chi-square tests. All of those are pretty common, and you'll find them in the literature. And this is just an example of what that 5-point scale might look like. 5-point scale is very common, but you can have any number of divisions that you want. There should be some reason you pick some division. And one of the most basic things to agree on is whether you want an odd point where there's a neutral category, or maybe you want an even one that forces people on both sides of the fence. And there are some other considerations that people really agonize over who think about this kind of stuff. So, yeah, here's what some data would actually look like if you summarized it in a table, where you tend to have some frequency distribution of responses. So the question today is, how do you handle this data to visualize it? So that's what we're going to do. And I'm excited to show people who might be analyzing this kind of data, this data set. Oh, I don't want to show you that yet, because that's the good stuff that we'll get to. If you want to follow along with this, every person should be able to follow along with this. Let me just show you where that is. If you go to the schedule, I'll just drop the link in the chat real quick if people are inclined to do this. Drop it in the correct chat, which I'll come around to. There we go. And if you click on this files link, it should open up the GitHub page. And what you'll see is a couple of files here. I'm just going to make a brief comment about setting up this directory. This is a directory that's very simple. It's a minimal kind of directory that I would set up for any project. I have a rule of thumb. I would bother setting up an R project if there is more than one script in the analysis, or if there's more than one data file in the analysis. And I'll go ahead and set up an R project. What an R project does, when you open it in R, is I'm just going to, maybe I'm just going to close this to demonstrate this for anybody that hasn't thought about or encountered the value of an R project. Here's what this looks like in my local computer. This actually does happen to be in a GitHub repository. I've made the R project file. I've actually got a few more folders in here, but the folders don't have anything in them. The graphs folder doesn't have anything in it, and the data folder doesn't have anything in it. But I typically would make those kind of folders in a project. So I just made them as an example. Because they didn't have any files in them, they haven't propagated to GitHub. So as long as you save a file in there, they will. But my scripts folder does have a folder in there. I decided, rather than using some of the data sets on my hard drive for this demonstration, that I would bother to do some data simulation, and I'll briefly show you what the script looked like, and then I call that script from my Likert script. I'll show you how that works in a second. But first, the advantage of doing an R project is if I just open the R project, double click it, and I look at the files. One thing, this is a minor benefit, but still for new users, it is significant in that it sets your working directory to the directory where the project file lives. And in a GitHub repo, I can have many projects there and organize it as I see fit. So I like that attribute, especially for new users. The second thing it does is that it keeps track of any of the changes that I make, a little bit like GitHub does. And it saves it in the R history. So if you're doing some commands and you have a different session and you forget the clever thing you were working on, you can always go back and look in your R history and find that kind of thing. And there are a few other benefits I'm not going to go into here. So what I'm going to do is I'm going to open up the Likert R data. If you want to follow along, you'll need to download the script folder and put that R file file in a folder from where you're working. If you download the R project file too, you can just open the R project and it'll look very similar and you can follow along with what I'm doing. So I'm just going to click on the R file to open it, scroll up to the top. I've got a long table of contents because we're looking at a lot of the customization things. So I'm going to make this a little bit bigger so people can see and read it easy, but I probably will have to zoom in and out several times today to show the graphs. And if it's too weird with the magnification, let me know. Graphs do get weird when I magnify it a lot, so I'm not going to go crazy. Now we need to load several libraries to do this. We need to load one called ggStats. It has some dependencies, so I'll leave it up to you to navigate this. But once you open an R script in recent versions of RStudio in the last couple of years, it should show you what libraries you need to install with a drop down up here. So hopefully if you are trying to go along, you're already doing that. ggStats has some utility functions for the Likert function, and it does have the Likert function in it, I believe. So I'm going to load that. Oops. And dplyr is a data conformity toolbox to do data manipulation. So we're going to use that. And that's got a lot of dependencies. So if you have, you can set DEP equal to true when you do install.packages, and it will just install all the dependencies, or R will help you these days. RStudio is good at that. And then, of course, ggplot2. There was a time, some of you will remember, that I pretty much reject all tidyverse stuff, and ggplot is next to tidyverse, and it has some of the same annoying things that I find about the tidyverse, but I've basically given up. I'm just here to tell you I've given up, and I'm basically using tidyverse and ggplot all the time now myself. So with that confession, here's the first thing I wanted to show is that what I've done is I've created a data file. Now I do this quite a lot for real projects that have a significant amount of work that do data manipulation. In this case, the data manipulation is literally simulating some new data. If we just look at the data script, what I'm doing here is I'm setting the levels for a synthetic survey, and it's, you know, the kind of strongly disagree, disagree, neither agree nor disagree, merely agree, or strongly agree. Okay, so it's the similar kind of stuff that you would have seen many times. And then what I'm going to do is I'm going to simulate 6 questions. And I'm going to do this with the sample function. This has a random component, or pseudo-random component, if that means anything to you. That's what computers use instead of true random, which isn't possible in computing until quantum computing comes along and allows us to do that. I'm going to set our seed. I'm going to create a data frame by simulating from my Likert levels 150 subjects, and each time I'm going to replace the values, of course, because each subject can choose any one. So I'm just going to go ahead and run that. 3, 2, 1. I've converted everything to factor with mutate at the end, and and I'm going to create a different one. It's called Likert levels don't know, and it's exactly the same as the original Likert levels, but it adds a don't know. It's just is one that's a common one, and there are some tricks in the GG Likert that I thought I'd show you that have a don't know category or an even category. So I just thought I'd mess around and do that too. And then what I've done is I've made the same data frame with the don't know data set. And then if we look over here, what I'm going to do is just clean that. I was just demonstrating what this script does. What I really want to do is that I don't really want to go to the bother of looking in this script once I wrote it, and I don't want to pollute the top of my analysis script with it either. So oftentimes what I'll do if I have a utility script like that, I'll make a scripts folder and I'll just call it with the source function, and the data will just pop up in the environment. And you can just watch that happen right now. 3, 2, 1. There we go. So what this is my data frame, my six um, my 6 questions and 5 factors. This is just the regular Likert scale. Then my 6 questions with 6 factors, including don't know. All right. And because I've done the set seed, you'd be able to consistently make the exact same data set every time as long as the seed is the same. And if we just want to see what they look like, we can explore the regular data set levels and the don't know levels. It's exactly the same, just adds the don't know category. Let's just look at the first few rows of one of those data sets. So you can see this is in the Tibble format. It's the tidyverse default data format. We can see for this first subject, now this is in a tidy data format, and this is a typical one for surveys like this. This is a typical arrangement for the data where you have the response for each subject. So this would be the first person surveyed, and you have their response for question 1 and the response of every person for question 1 in the first column, question 2 in the second column, and so forth. This is in tidy format because each subject is independent of each other subject, and they're organized by rows. And then the columns are the features of the data or the features of the questionnaire. So this is typical for any data and for questionnaire data in particular. Notice that I haven't converted this to numbers or anything. We're just visualizing this, and it's nice to have these labels here. As you'll see, we can use them to actually create information with the graph framework. And the very first thing I want to show you is my favorite part of this whole package. And it's just that you can call it on a properly formatted tidy data frame without doing anything else, and it will just make a nice graph. A note that this plot does not have, or this data set I made doesn't have that many questions. Typically, questionnaires have like, more questions than 6, and they often lump into the data file things like demographic data, which are not really included here, although I will show you some examples of some demographic grouping variables in the script. But have a look at, nevertheless, for this small data set, just what calling that one function with no options whatsoever on your data frame gives you. 3, 2, 1. Oh, it didn't find GG Likert. Let's see. Oh my goodness, did I not run something? Let's see. There we go. That was a Dynamo. There we go. Now this is a pretty good graph, and this is the kind of graph that would take me 10 or 20 lines to construct in R using a library I can't really remember the name of, which I used for many years for this kind of data. But this is pretty nice. Let me walk you through some of the details that I like, and I'll only do it for this first one, and then you can stay with it for the rest of them. One thing I really like is that we've by default got the percentages of every category, and because there is an odd numbered category, the function has assumed that we have a two-sided agree and disagree, or a binary kind of classification system here, which is the default for designing these kinds of surveys. And it's also given us percentages for the disagree and the agree in the margins. It is also picked by default a color scheme that that distinguishes between the two sides of the center. This may not always be the case, and I'll go through some examples where we can alter the behavior of this to do this. It's also labeled the at y-axis with our headers for the questions. Now you can, and I've seen this in data frames. I've seen people actually put the text of their question in those column headers, but that doesn't adhere to best practice in R for tidy data sets. That's one. But also it robs us of some of the neat functionality in the liker function to edit these labels, which I'll also show you. It makes us a nice legend that goes with every unique answer. I guess the thing that I would like to add here is that I've created because I've simulated this data, I've created a perfect set of labels, but I often find that there are typos in there. And so you would, at this stage, if you just did it quickly, you would need to, for most data sets, fix the typos if there is any variation in your labels. Anyway, I think this is a pretty good graph. And the idea of centering it on the neutral response is so that you can gauge visually the size and of the agreement or disagreement relative to each of the questions very easily. And this is the traditional way to summarize this kind of data. You can compare across questions, you can compare across categories, and as you'll see, we can compare across groups and other kinds of things. So I'm just going to go through really the detail on how to do that. Let's see if I can get away with making that a little smaller so we can see the code at the same time. Now, one thing we might want to do is, especially if you have a lot of questions, is curtail the number of questions that you look at the same time. And we can do that with the include function. And by the way, top tip, when you're learning to use a function like this, if you just put your cursor anywhere in the function and hit F1, we get up the help page. And if we do that, we're able to look at the definitions for these arguments, and the definitions are usually down below in more detail. So it in tidyverse syntax will allow us to put the variable names. The colon is this nice shorthand in tidyverse. It is something nice in tidyverse that allows us to do ones that are consecutive in some way. So you could put the name of any variables in there, even if they're not alphanumerically sorted, and it would still do the same behavior of giving us all of the variables that occur. The reason it can do that is because the column headers are treated as labels, and internally R sorts them as numbers. So it's quite a neat little trick, and that's why it works. Okay, so we're going to go back to the plot. We're just going to look at, we can curtail the y-axis, 3, 2, 1, down to 3, just 3 questions there. If we want to set our colors, we would start with the function call and use that ggplot syntax. We could add a title. I really wanted to say that we could use the brewer, one of the brewer functions. So if you've used R for a long time, you might be aware of color brewer, which allows you to pick certain palettes. And this is one of the color brewer palettes that consists of red, yellow, and blue. So we can just apply that to our Likert data, 3, 2, 1. I mean, this is a bit garish. It's like the candy-colored clown of Likert color scales, but it's just for the example that you could use. And you'd want to manipulate that for creating visual consistency across the graphs in your paper, and maybe different color schemes for different parts of your instrument and so forth. Some people, for instruments like this, don't like to look at this jagged sea of stacked columns. And instead, they would like to sort the responses from agreement to disagreement. And an example of why you might do that is, what if you, within one category like organization for the National Student Survey, and you wanted to see which question was perceived by the respondents as least organized and which was most organized. Well, you might sort with the sort argument. So we can just kind of have a look at what that looks like. 3, 2, 1, back to the original colors. And we can sort based on these quantities by doing that. Now, you might notice, well, what is this actually sorting on? What is it actually sorting on? Because this one doesn't look like it's sorted down here. And I caught that when I was going through this, and it took me a little bit to figure out that it's sorting on the proportions. So this is 67, and that's just 65%. You can see that in the margin, of course. But you do have some options, it turns out, for a sorting method. So if you have the sort method argument, there are a number of ones that you can look at. And, again, you can examine that on the help page if you want. So we could, for example, sort it by the mean number of responses, 3, 2, 1. And then it looks, these have switched at the bottom, and it looks like it's properly sorted now to the eye. Well, except for this one. So always an exception to the rule. We can also switch the x-axis order. So here, if I just bring this out a little bit, we've got from disagree to agree, but there might be some reason why you wanted to reverse it and do it the other way. So we can use the reverse liker. This reverses the given scale in the data set. So 3, 2, 1. And it reverses the colors as well. And likewise, we might want to do something with these labels. These labels, I find them pretty good. I really like the way that the labels are laid out by default. But we may want to remove them and add our own labels or something like that. So we can, with the add labels argument, which by default is set to true, we can remove them by setting it to false. 3, 2, 1. Oh, that didn't seem to remove the, oh, I see. It removed the interior labels. Yes. Okay. So we can customize those interior labels as well. I like this. I think you'd want this if you were making a large number of visual comparisons all at once, but some people still might want that numerical detail and might want something done. So anyway, you can manipulate the size of the labels, the precision of the or the accuracy of the decimal accuracy, that is, whether to hide overlapping parts of labels, and what the color is. So let's have a look at that. 3, 2, 1. There we go. And I guess for some that are too small, some default margin for that hiding. I didn't play around with that too much. There are other ones we can do. We can we can tweak the margin totals. Keep your eye on one of the totals for the margins, 3, 2, 1. So they've changed, and we've got some sorting added on here. And now what there are some tricks that we can do, and by default, see if this is correct. By default, I believe that these margins on the side reflect the agree and the disagree. But if we add this up, we can see that when I've set the sort proportion include center equals to true, we can see that this doesn't add up anymore. And what's happening here is this argument allows us to divide the center for the odd shaped Likert scale and add it to each size. And that's a common thing that you see so that the totals add up to 100. Because otherwise they of course don't. And again, we can just customize what those look like. 3, 2, 1 in these margins for those totals. So you see how flexible this is graphically, and actually just how easy it is to do this kind of thing, even something modest, and do these margin totals. Probably would have taken 20 to 25 lines of code before this solution came along. So I'm a big fan, as you can tell. I've suffered through so many of these analyses. Now, you can actually remove these margins completely by the add totals argument, 3, 2, 1. So we're back to the default graph without the margins. And I think that's all of the totals tricks and labeling numerical summary labels that that I went through. Maybe some more will pop up in a little bit. But now we're moving to another topic, the topic of the question labels. So you'd be laughed out of the psychology journal for submitting a paper and have your questionnaire y-axis look like this with Q1, Q2. Something that I note, it's a stylistic thing that I find, at least I found it extremely jarring until I saw enough of them in print, was that psychologists and economists and other people who use questionnaires a lot in their science, they just love to have enormous labels for their questions. They love to have the explicit question in there, and the questions are seemingly as long as possible. Anyway, I haven't gone to that extreme, but we probably would want to change these labels to something that makes sense so that the viewer of the graph can get the information from it. I've just put some silly ones in here, first question, second question, and then an example of a longer question to label the first few here. So let's have a look at what that looks like. 3, 2, 1. Oops. There we go. And then let's print it. Okay, it looks a little jagged because of the magnification, but if we stretch it out so that we can read it, what we can see here then is that we've just added text labels. And just note a few things we'll go through in the next few examples that for this long label, there's an arbitrary wrapping point that's right justified, and you can edit and customize every point of that. You can edit and the justification. You can edit the wrapping points, and we'll look at a few of the options in the next few bits of code here. Let me find where I'm at. Here we are. So one, you can update the labels in a live way by calling gglikert, passing your data, and then just adding in the variable names with your custom labels. So we've already got a version of the graph here, and we're just going to update the label for Q1 and Q6. So keep your eye on those. 3, 2, 1. So now we've got an alternative label for the first one and a custom label for the sixth one. This is the kind of thing that it actually emulates the behavior of updating models for fairly advanced statistical methods. And because of that, I'm really familiar with the way this works with a ggplot layer approach, just updating your model. I really like that. We can edit the label wrapping with the y label wrap argument. So we can make the breaks small, 3, 2, 1. And this is much more aesthetically pleasing than the long one to me, or we can make it much longer so that it has to be a straight question, 3, 2, 1. This is my least favorite one of all because it just looks stupid, especially compared to the other ones. But I do see both of those, and it's nice to have the options. Another common one, if you can bear with it being scrunched up for a second, is, let me pull it out to just say this before I run that. Another common one we might want to do is, depending on what scale you're going for, it's real common to make a cutoff for what is considered positive versus negative as a sentiment in a particular question. And you would design your questionnaire to be able to do this. For example, in the student survey, the National Student Survey, it's agree and disagree in exactly this kind of Likert scale. but all of the analyses and summaries, almost all of them that are published, consider neutral, agree, and strongly agree as positive, and the other two as negative. So they've made a judgment called to group the data in that particular way. So how do you alter that? Well, you alter it with the cutoff. This will look better in just a second. And you just say, well, if there's no negative categories and you want them all to be considered shades of positive, 3, 2, 1, you might do it like this. Oh, I don't like that long label. I'll pull it out just a little bit. If you want one negative, you could set cutoff to 1, 3, 2, 1. You can actually put in decimal values. So if there's some category, let's say like the neutral category where you neither disagree or agree, for ours that has 5 responses, you could put in 2.5. Then it would categorize half of that middle category as disagree and half as agree, but you could do it with any arbitrary decimal. So I'll just go through 1.25 and 1.75321. That's 1.25. Keep your eye on a number on one of the bars, 321. So some of them change, some of them don't by such a small amount. For 3 categories of the cutoff, or for all 5 being negative. So, you have full control over this. Likewise, you can control the symmetry of the x-axis. Notice how it changes. I didn't point this out earlier, but when it's all negative, we're going from 0 up to 100% for all of these. And you can control the symmetry of that and force symmetry on it. So if we put that cutoff back to 1, it'll still be very skewed. Just to have a look at what the non-symmetrical x-axis looks like, but we can force symmetry with a symmetric argument. So just keep your eye on this axis or the bars, 3, 2, 1. So you see it just scrunches it up so that you have a accurate representation. This would be most useful if you had multiple panels and you wanted visual comparison between panels that might not have the same X scale. So that's a nice little, again, this is another thing that would take lines of code to sort out and be janky for different ones. So I really, really like this. We can customize certain values. Let's look at that other data set that's got a don't know, 3, 2, 1. So this has that don't know category. Some of the responses don't have all of the categories, but most of them do in the data set. What's simulated a data set of a certain size, and just by sampling error, we don't get all of the ones for all of the questions, which is kind of funny. We could drop this or any category if we wanted to make a graph that drops the don't know. So this is using a little bit of dplyr kung fu, but what we're doing is I'm mutating this data set also to have a factor, but instead of mutating it for the factor levels for the Likert underscore don't know, which is this one, if I bring it out, I'm actually factoring it according to just the plain old Likert levels without the don't know. This is kind of a little bit of a minimalistic programming trick to filter out the don't knows and convert them to NAs. So 3, 2, 1. And we get back, the survey without the don't know values. We can also exclude any category in this way by using exclude fill values if you want to explore certain subsections. So this does exactly the same thing as this graph. So if I just sweep out the graph, no, I'm gonna leave it. It won't be very good to look at, but trust me, if you can see it blink, 3, 2, 1, did make a new graph. And it's the same way of excluding the those categories. And then the last thing we do is kind of an advanced thing, and it has its founding based on particular kinds of graphs for statistics, for linear models. At least that's the first time I came across what is now called facets. And facets is a part of, it's not a big part of ggplot, but and actually, unless you're doing some serious linear modeling, um, facet graphs were kind of ugly and old fashioned a little bit, and so they're not really that fashionable these days. But for diagnostics, they're very powerful for some statistics. And one of the reasons they're used is it makes it very easy to compare um, different graphs for exactly the same information, holding all the scales the same so that you can do a direct comparison. So there are some facets tools built in. And to explore that, I'm going to just on the fly here, I'm going to create a new version of the data set called data frame underscore group, just starting with the original data frame, 321. So that'll pop up in the global environment now with the group. And then I'm going to add two different group variables to that data set. That one is going to be it's going to allocate each person, each subject to group capital A or group capital B, and then a second one that allocates them to group lowercase a, B, or C. Okay, so I'm just simulating some subgroups in this to show you some of the functionality with the this facets, some of the facets tools. 3, 2, 1, boom, boom, and then I'm going to use the DF group to graph all the questions, but I'm going to use facet columns argument to create different graphs side by side for that first grouping variable. I'm just tweaking the label size. 3, 2, 1. Of course, we'll need to make this bigger. And this takes these two groups. And if you do have demographic data, you'll want to be doing this. And let me tell you, this would take double the code. Yeah, I think you should. I mean, this is not a very old it's not a very old library. And like I said, doing this, the graphs look great even with very little customization, and it's so easy, and it's appropriate for every single questionnaire any of those guys will do for their projects. So yeah, I'd recommend teaching it. You can actually do facets on all the groups. You can go crazy, 3, 2, 1. So we're not going to be able to see this very easily on this, but this is for, it's got columns for the group one, and then it's got rows of columns for the second group two. So it's quite good. And I guess the last little thing I'll go through in the last few minutes, I'll do it quick because we're out of time, is the idea of a stacked bar graph. This is just a straight bar graph that doesn't represent the proportions of respondents. These are real popular. They're considered a bit old-fashioned, at least the old style where they're vertical bar graphs that are just stacked on one another. But I find these very aesthetically pleasing, and they also are very informative. So you can quite easily tell the difference in proportions of the R. And I find this even a little nicer to look at than the centered on the neutral values. Okay, so I'm just going to go through a couple of these examples. We can customize this by sorting it 3, 2, 1. In the same way, I've taken off the labels there, and you know the labels become a little burdensome. You can do the same thing with facets. So this does facets by questions, comparing the groups. So this is convenient to compare individual questions between groups. And then one of the last things here is to simulate some weights. If you wanted to weight certain parts of your survey, you might weight them by some factor to correct known bias. You might weight them by the number of respondents. So I'm just creating some fake weights here just to demonstrate it. and then I've just rolled those in with the GG Likert by setting the weights to my sampling weights. And by the way, the sampling weights are just 0 to 1 weightings. And you wouldn't normally have weightings like this. You'd normally have them for different subgroups, possibly. And then the very last thing is just, I'm not going to go through the technical details of why, but we can do stacked data instead of wide data to do faceted bar plots like this. So if you want to compare a lot of stacked bar plots for a lot of questions with no labels, you might rearrange your data to be a slightly different format, a long format, and do it. And with that, boy, that looks terrible without doing the screen. That's all I've got. I've linked to a vignette for this package, which I'm a big fan of. It's on GitHub. And then if you really want to learn about categorical data analysis, the classic book is by Agresti, and I think this is the most recent version as well. Yes, yes. If you have some sort of control for the weighting, yes. Let me see. One of your questions said is use attitudes as negative to ensure your participant hasn't just clicked the same response. Yeah, I mean, I think you'd use that in exploratory data analysis, and you might even use that to inform some weights. I think the kind of thing you're talking about is like there's an artifact in the National Student Survey that that has outliers. That this is one of the things I actually have written a paper about this with my friend, and then we just kind of stopped working on it because we were really sick and tired of working on the national student data, where you'd get some responses that were all the most negative response, or some that were all the most positive response, and so they weren't informative surveys. And what you might do is, you know, do something to either point out how frequent those bogus ones are or not. Another classic is people, if I say Christmas treeing their answers, it's a way of calling, you know, haphazardly picking different questions. And there are very common and simple to implement statistical methods for detecting haphazard responses based on the how common certain responses are in the rest of the data set. So yeah, you use visual techniques, but you probably wouldn't use this. You'd probably use kind of exploratory data analysis to do that. That's all I've got. As usual, I'm going to rush down and be with my family a little bit at this hour on this day. My daughter is coming home for dinner tonight, so I'm very much looking forward to that. I'm going to stop the recording.